Okay, so now I'm going to, I think, cover the next couple fairly quickly. Once again, these problems, the sort of fundamental idea here is what forces are acting on something at any given time. So number 8, a pitcher throws a ball, whizzes through the air on its way to the batter. What are the forces on it? I've drawn the velocity of the ball in here. The only force on the ball after it has left the pitcher's hand, meaning at the instant the pitcher's hand is here, some distance is in between them. There's, I guess, the rest of our pitcher, well, his arm anyways. So once the ball has actually left his hand, there is no force of the throw or anything like that. There is no horizontal force anymore on that ball. The ball has a velocity in this direction, but there is no force on the ball horizontally at this point. Vertically, the only force on the ball is the force of gravity. Due to the force of gravity and the inertia of the ball, which attempts to carry it in a straight line in this direction, the ball's actual path will be parabolic. And assuming it's thrown slowly enough, falls short of the batter. In general, of course, a baseball is thrown fast enough that it has dropped only insignificantly by the time it reaches those 90 feet to the batter. So, fundamental ideas here: once you've thrown the ball, the only force on the ball is the force of gravity. This is, of course, neglecting air resistance, as we often do in physics, where we ignore friction and air resistance and water drag and all of those other things. If you were to add in air resistance, then that air resistance force, if you did account for that, would be heading in the opposite direction to the velocity of the ball, and that would be the only horizontal force on that ball. Our blocks sitting at rest on the horizontal table, are the block and the table interacting? Yes, of course they are. The block is putting a downward force on the table as a result of gravity. The table is putting an upward force on the block. They're not, in either case, experiencing a net force. Neither of them is accelerating in any direction. And finally, the problem of the elevator. Earth exerts a gravitational force downward on the elevator of 150 newtons. The elevator is moving upward, pulled generally by a cable, and it's moving upward. This vector here indicates the direction of motion. Yeah, I can spell. The motion is upward at a constant speed. I'm underlining constant speed and highlighting this idea, constant speed, or constant velocity is other language you might see, because constant speed means no acceleration, which means no net force. Because there is no net force, if gravity is putting a downward force on your elevator of 150 newtons, then the force on the elevator provided by the cable, that's this force here, must be 150 newtons. It must be 150 newtons because there can be no net force on the elevator itself. If there is a downward force by gravity of 150 newtons, the upward force by the cable must be 150 newtons. They are opposite in direction, they are equal in magnitude. I'm emphasizing this because one of the standard misconceptions people tend to have is that if something is moving upward or downward or in any direction, if it's moving, then there must be a slight, ever so slight, larger force in the upward direction, they'd say maybe 151 newtons or 150.2 newtons or some crazy number like that. If this number, the upward force in the cable, is anything greater than the force of gravity downward, then we will get a net force greater than zero. We will get an acceleration which is greater than zero. It might be tiny, but it will be an acceleration, and we will no longer have constant speed. If we have constant speed, acceleration is zero, net force equals zero. Don't be fooled by those problems. And that is it. I will see you all on Thursday.